Okay, in this scenario, you imagine somebody's forearm or wrist gets hit with something and begins to swell. So this happens, let's say, at noon. So after 0 hours have passed, the swelling hasn't happened yet since it's just been hit. And so that swelling is 0 centimeters. Now, after 1 hour, so now it's 1 o'clock, the swelling has increased. So there's like a little bump on the arm, and it's 0.15 centimeters. At 2 o'clock, the swelling has gone up just a little bit more to 0.2. Then at 3 o'clock, so another hour has passed, the swelling is actually reduced back down to its 0.15 centimeters, and maybe there's some ice on it. And then at 4 o'clock, it's back to a normal. So it's a very brief swelling period. So x is the number of hours, or since noon, and f of x is the height, the maximum height of that swelling. Okay, in this scenario, we've got an elevator here that's currently on the first floor. It's going to be traveling all the way up to the 4th floor, passing through the 2nd and 3rd floors. We're going to hit a stopwatch when it starts moving up, and we're going to see how far it travels over time. So right at the beginning, it's traveled nothing, but after 1 second, it's moved up 3 feet. Okay. So that was after 1 second. Okay, after 2 seconds, we're traveling all the way up to 7 feet. So now we're up higher. After 3 seconds, we're all the way at 12 feet. Okay, we're gaining. 4 seconds, we're going to go to 18. 5, we're up at 23. 6, we're to 27. And 7, we hit that 30-foot mark. Okay. So if x is the time in seconds, and f of x is the distance that the elevator is off that ground, ending up at a distance of 30. Okay, in this scenario, we've got a billiard ball, and we're going to be hitting it against this bunker back here. And right now it's 4 feet off the wall. Right when we hit it, we're going to start that timer. Right now it's at 0. So at 0 seconds, it's 4 feet away from that bunker. We hit it, and after 0.2 of a second, so very brief, it's moved up, and now it is 3 feet away from that bunker. Okay, and then after 0.6 of a second, it's actually only 1 foot away, so it's moved up here. So we might be watching this with a slow motion camera. Now it's only 1. Now at 0.8 of a second, it's actually touching that wall at 0. And then at 1 second, it's actually bounced back again, and it's 1 foot off again. So, and then at 1.2 seconds, it is 2 feet off. Okay. And at 1.6, it's actually all the way back to the 4 foot mark. So if x is the time in seconds, and f of x is that distance that the ball is away from that bunker. Okay, in this case, we've got a space shuttle which is launching off of its launch pad, and we're going to be looking at how far off the launch pad it is over time in seconds. So right when it launches, we start the timer. So at 0 seconds, it hasn't risen at all. After 2 seconds, however, it's 6 feet off the launch pad, so it's raised up. A total of 6 feet, and the feet are off by 6. So we'll go off the nose 6 feet off. Okay. Now, after 5 seconds, it's actually risen up to 37.5 feet. So it's clearly accelerating. A total of 37.5. After 10 seconds, it's gone up quite a bit more. We're going to go off the page here, but I'll tell you that it went 150 feet. And finally, we have a measurement at 20 seconds, so that was after 10. After 20 full seconds, it goes up even further, 600 feet. So clearly it's really accelerating. So if x again is the time in seconds and f of x is the distance that it's rising up off the ground. Okay, in this case you've got a person with a ball that starts at an initial height of 4 feet and he's throwing it up in the air. So at 0 seconds the ball's at 4 feet. Now he tosses it in the air, okay? And after 1 second, after half of a second, okay, the ball is already at 16 feet in the air, okay? 16 after half. After 1 full second, the ball continues to travel up 20 feet, okay? Continuing down, so that's 20 so that's a half second at 1 second, 20 feet, okay? At 1.5 seconds, the ball starts coming back down and is again at 16 feet. And finally, we have the data that at 2 seconds, it's back at 4 feet. So if x is the time in seconds and f of x is the height of the ball. Okay, we got a bungee jumper here. And the initial height of the jump is 220 feet. 220 feet. Okay, so jumps off at 0 seconds, it's 220 feet. So that's right when you start the stopwatch. The person jumps off, and after 1 second, okay, there's that rope, they're at 200 feet. Okay, so 1 second has passed. 200 feet. After 2 seconds, okay, the person's plummeted a little bit further. After 2 seconds, they're at 160 feet off the ground. Okay. 160. After 3 seconds, $180. Okay. So their cord must be getting tight. After another second, they're down to 190. Okay. And then after another second, they must be bouncing back up. They're shooting back up to 180. And last but not least, after 6 seconds, they're back up to 175. So they're up a little higher. So if x again is the time and f of x is the height off the ground. Okay, in this situation, we've got a man who's going to be running around a circular track whose diameter is 100 feet. Okay, and we're going to let x equal the time in seconds. We're going to start a stopwatch when they start running. And f of x is going to equal the person's distance from this wall here. So we're looking at this from above, like a bird's eye view. And we're looking at their distance away from this wall. So after 0 seconds, the person is 0 feet away from that wall. Okay. Now, over here, it's a quarter of the way around, and that actually takes 2.5 seconds. Okay. And that distance right there is now 50 feet. He's 50 feet from that wall. Okay, after another 2.5 seconds, so this is total 5 seconds, right? It was 2.5, and now the timer's still going. Now it's 5 seconds. He's 100 feet away from the wall. Another 2.5 seconds. Now again, he's 50 feet away, so after 7.5 seconds, right? A little bit more time's passed. He's 50 feet away again, and then after the full 10 seconds, he's back to 0. So if x is the time in seconds and f of x is the guy's distance away from that wall. Okay, in this case we've got a chair with the leg of the chair. So this is the thing we're concerned with here. I've blown it up here. So this is the leg of the chair, and what we're interested in is the diameter of that leg over the course of a day. Usually temperature fluctuates throughout a day, and therefore things expand or contract, and therefore the diameter of something made out of wood or any material will expand and contract. So we're looking at the diameter of a table leg over the course of a day. Okay, so let's say we're starting it at 6 a.m. Okay, so that's hour 0. We're starting the timer there. And let's say it's 4.36 centimeters. Okay, now move up to 9 a.m. And now, so that's after 3 hours. Now we're up to, it's expanding a little bit. Okay, it got a little warmer. Now it's up to 4.75. Now we're going to go 5 more hours later. 2 p.m. It's warmer now. 8 hours, so after 8 hours, now we're up to 5. So it's expanded even more. Okay. 2 hours later, we're cooling down a little bit. 10 hours after we started. Now it's back down to 4.96, so now it's contracting. And finally, we check it an hour later at 5 p.m. and it's at 4.91, so it shrunk even a little bit more. So x, again, is the time, and f of x is the diameter of a wooden table leg.